In the last video, we look how to rotate an object around itself and around a fixed point. We conclude that the transform.RotateAround is the best and easy choice when working with these two movements. The link to the video is in the description. We get in a point where we want to rotate an object around other, but with a different trajectory angle. In the screen now you are seeing the blue planet rotating around the sun, the yellow one, in a yellow trajectory. That trajectory is a diagonal trajectory we will do here in this video. In the last video, the blue planet was making the blue dot path using the rotation around function. And this diagonal movement I call trajectory movement. And the other movement that is missing is the rotate towards, where a game object rotates around itself, looking to another object when the last one moves, like a torrent rotates towards an enemy. In this video, we will solve this problem. These videos are based on the article from the John French. Go to the link in the description and learn more reading his post. Let's dive in. First, we analyze the rotate towards. Here I have a rotate towards class, a monobehavior one. This has the transform of the target, has a speed and a step that we work with the time.delta time, and I have a direction that we will calculate inside the code right now. I have the update function, and inside it I have two methods: the quaternion rotate towards, that is a method that uses the quaternion rotate towards function, and a vector3 rotate towards that we will see in later. Here is the quaternion rotate towards functions. It has the step being used together with the speed and time.delta time. And here we calculate the direction using the target position and the transformed position to take the direction from the target to the transform position of this object. I have made this comment here because I was curious about the looking rotation and the quaternion.Euler that we used in the last video. So I thought if I can change the look rotation by the Euler one, but it's not possible because the look rotation uses the vector up as a parameter. So when we use the direction here, it will consider the up direction as to make the calculations. But I did some good approximation, so I think that somehow I can make a function to imitate this. And here we have the transform.rotation using the quaternion rotate toward functions, and this function has the transform.rotation of this object, the direction angle that we calculate in this line here using the look rotation, and the step that make it rotate smoothly. I think that these movements is very simple because we have just 4 lines of code, and all the functions here is very straightforward what we are doing. If you look here, the rotation, the look rotation, we have it's create a rotation with the specific forward and upward direction. So let me show you this inside the unit, but first let's see here the rotate towards from to towards our object. So here we are taking the direction of the target and the position we want to look up towards up, and here we are using the rotate towards to rotate to that new direction. So let's show you. Here I create a simple scene when I have this arrow, and he is the yellow target. In the arrow I put the rotate towards and assign the sphere as the target, and the step I put equals 0 and speed equal 20. Here we can see the two functions in action. The first function is the look rotation. So here when I rotate my yellow sphere, this distance here will take a direction from this point to this point. This is what the look rotation is doing. And then when I change my yellow ball to a new direction, the arrow here rotates towards using the rotate towards function. Very simple and straightforward, or towards. Now let's look at the vector 3 rotate towards that use the vector 3 to rotate towards an object. Here we have the first two lines equals in the two functions. First we calculate the step using speed and time dot data time, and the directions, the tag dot position minus the transform dot position. And here we need to calculate new direction using the rotate towards. And in this point I get a little upset using this method, because different from here, when you use the quaternion, we first look to the rotation, then we apply the rotate towards. Here is a little different. We rotate towards and then look rotation. This is a little different, and I prefer the first one. For me, it's look more natural to think like that, not the contrary, but it's a taste preference. You can choose anyone. And here we are using the transform forward. This is a little different because here we use the global transform rotation of the game object, but here we are using the transform forward because we have the arrow here, and the arrow is pointing in this direction, and we need to rotate and make the arrow face the yellow ball using the blue axis here. The other things are equal, so we have the direction, a step, and we have this extra parameter that I set is equal to 0. In the documentation it sets to 0 too, and it has no clear explanation why to use this parameter. And actually I even tried to change anything here, just set to rotate towards. You can make some changes here and see what happens. And then I will transform the rotation here using the quaternion look rotation, passing the new direction, and the effect is the same as you can see, so you can choose anyone you want to use anyone you feel comfortable with. And now we will try to use the rotate in trajectory and try understand what is happening. In the first video I show you how to rotate this blue planet around the sun using the rotate around, and it will rotate around the sun making a horizontal trajectory. But if we want this object to make a diagonal trajectory using the around rotation, it will not happen. It will rotate in a horizontal movement above the sun. That is wrong. So here I have a rotate trajectory script. This is a mono behavior. This has the transform of the sun, the speed, an angle, and a trajectory. That's the same the direction of the other script I used. And here don't take it in account, because this is something that I use to make a testing here, as I showed before and I show in the future. And inside the private the start, I set the trajectory being the transform position minus the sun dot position. The trajectory is the direction we want the planet to rotate around the sun. Don't consider the orbit being applied to the trajectory here. And I have a rotate look rotation inside the update. This is a custom function, and inside this function I have a vector 3 called orbit. I need to assign it because I need to use it here if it cannot be null, so I put it a little forward from the sun. Then I use quaternion.Euler multiplied with the orbit. And here, different from the last video, in the last video I do not use that part. In the last video I show you that quaternion.Euler transforms a vector 3 in a quaternion angle. So I show you that transform.rotation is a quaternion, and using the quaternion Euler with some vector 3 rotating in 30 degrees, and in this case multiplied by time dot delta time multiplied by speed, it will give us a rotation, a quaternion angle to the transform.rotation. But when we have a quaternion.Euler multiplied by a vector 3, that in this case is the orbit, this creates a new function. That new operation is this applied in the left of the vector will rotate this orbit vector in angle values, and we reapply this new vector to orbit. So what is happening here is that this is working as a function that rotates this object, this vector 3 to a new position. So quaternion.Euler, when applied to the left side of the vector 3, rotate this vector some degree. Then we are using the quaternion.look rotation, passing the trajectory, and then we can see it, this concept used here again. This is a property of the quaternions. So when we have some quaternion in the left side of the vector 3 multiplied, it is rotating this vector by some vector, in this case the trajectory, and we reassign it to the orbit. Then we use the angle, we increase the angle utilizing the speed and time dot delta time. We make the angle stay between minus 360 and minus 360 and 360, and then finally we apply the transform, so our object can rotate around the sun by the orbit we establish, by the direction we establish. So the key point here is to see that when we have a quaternion alone and we pass a vector 3 inside this function, it will rotate and give us a quaternion angle, so we can assign it to a new quaternion or another quaternion. But when we have a quaternion multiplied by the left side of the vector, it will rotate this vector by this angle here, and we can reassign it to a new vector 3. And so the quaternion has these two amazing mathematical properties we can use to rotate our objects. One is to find some angles and assign it to a new quaternion, and the other is to rotate a vector 3 to a new vector 3. This is amazing. Let's see it in action. So in the beginning of the game, we calculate the direction between the planet and the sun. So the direction is this one. We cannot reassign here because we need to change it by code. So let's restart it. Reassign to a new direction. And when we play the game again, the new direction will be set up. But we can change it by code, of course. Now we get to the end of the little series we have here about rotation, and I ask you to subscribe to the channel and please give a like to the video. This motivates me to make more informing videos like this one. Thank you and see you in the next one. Cheers!